Hi, I am Pratyush Das from the Institute of Engineering and Management in India. Before I begin my talk, I would like to give a small disclaimer that I am a CS undergrad and not a physicist. So, this talk is a completely personal account from my own experience of writing software for high energy physics. What is high energy physics? Perhaps you will be more familiar if I said particle physics. High energy physics explores the fundamental particles that the world is made of and their interactions. High energy physicists try to answer the big questions like what is the universe made of? What are the forces that govern it? Something that might be surprising to the audience is that high energy physics has some of the largest scientific collaborations in the world. For example, the CMS and the ATLAS experiments that are located at CERN have around 3,000 people affiliated to them. Just imagine 3,000 people working on solving the same problem and collaborating with each other. Something most people probably do not know is that the first computers were built for use in physics research. When I say this, I'm not really talking about the secret computers that were used for breaking secret codes and used in the wars. Uh, so John Vincent Atanasoff and his then graduate student Clifford Berry created the first electronic and non-programmable digital computing device that they called the Atanasoff-Berry computer. They created this in 1937, and it was quite popular, or the considered the only computing device till 1942. This was then replaced by ENIAC, which was inspired by it. ENIAC was initially developed for use in ballistics, and it was developed by another physicist, John Mauchly, and J. Presper Eckert. This is something that the audience might be more familiar with. I would ask for a raise of hands if this was a live presentation, but I assume a lot of people in the audience have heard of Monte Carlo techniques. This was invented by Nicholas Metropolis's group at Los Alamos National Laboratory for physics problems. Most computer science people would have heard of the von Neumann architecture that forms the basis of most computers today. It was developed because John von Neumann, someone who played a major role in physics research, his internal memo about using the ENIAC for nuclear simulations was leaked. And then something that is more close to my heart, in 1991, Tim Berners-Lee invented the World Wide Web at CERN. Before I go into how we use Python in high energy physics, I would like to talk about what are the biggest computing challenges in high energy physics. High energy physics research generates a lot of data. Elementary particles travel extremely fast. I mean, I guess we are taught in our physics and chemistry courses in high school about how fast an electron moves around the nucleus. And try to imagine about how many interactions there would be between different electrons, and each of these interactions need to be stored. But it's not just the size, it is also the complexity of the data that needs to be stored. The representation of the particles and their trajectories and also their collisions, and that is not very easy. When I said that we need to store this much data, we actually do not store all of the data. Um, these experiments have a trigger system built in that rejects some of the data outright, but even then, it's petabytes and petabytes of data. Here I have a screenshot of a CERN webpage announcing that the CERN data center passed the 200 petabyte milestone, and this was back in 2017. It has been 3 whole years since this has happened. But even this is not really the limit of the data that we need to store. This data storage is going to increase exponentially when the Large Hadron Collider is upgraded to the High Luminosity Large Hadron Collider, or what is more commonly called the HLLH. And this is going to happen in less than a decade, so we really need to prepare for this. The high energy physics community has built something that I think is unique to the high energy physics research field, the worldwide LHC computing grid. It is a network of computers that are distributed all over the world at research institutes and universities where high energy physics research is conducted. This is used to distribute the data storage and computation. This solves some of the problems because the burden of storing the data or computation is not on one particular research institute. Then again, the WLCG is not enough to solve all of the high energy physics computing requirements. SI06 or SPEC in 2006 is an industry standard benchmark with a wide variety of codes represented. HS06 or HSpec06 is the high energy physics variant of it. It uses only the C++ base codes from SI06 that match high energy physics use cases. If you follow the plot on the slide, you will notice that there is almost a factor of 5 increase for SI06, whereas just a factor of 2 increase for HS06. This shows that for high energy physics use cases especially, CPUs aren't getting much faster. So what do we do if we can't use CPUs? Let's use GPUs. A lot of the high energy physics computations are embarrassingly parallel, which makes it ideal for using GPUs. CERN's extensive use of GPUs for high energy physics research also found a spot on the NVIDIA website. At the lower half of the slide, there is an excerpt from Adrian Uftiger's talk titled GPU Resources for the CNF HPC Cluster that shows that using GPUs could drastically improve performance for high energy physics problems. The awkward array library attempts to solve some of the problems that I discussed in the earlier slides. It was built with the need to perform computations on the complex high-energy physics data that I mentioned, and was also recently redesigned to have different levels of abstraction that allow multiple things, like possibly having a GPU backend in the future, and to allow someone who wants to play with the source code to have access to the underlying C++ layer. And most important to this talk, it is meant to be used via its Python interface that is located at the top of the design tree to the right of the slide. So what makes a language ideal for use in high-energy physics? It has to be easy. Physicists don't really want to spend a lot of time learning a new language. You have to remember they are not software engineering or computer science people and are usually not interested in the code itself. Python is easier to use and learn than most other languages. Okay, there are some purists who would probably say that Python is not necessarily easy if you want to use it properly and not be really slow, but let's ignore that for now. The language has to be fast. As mentioned in an earlier slide, high-energy physics has a lot of data, and to perform computations on that data, you need the language to be fast. Python is not necessarily slow. When used with libraries like NumPy and Numba, it can be quite fast. The language has to be mainstream. If a language is popular, it is easy to find resources to learn the language itself and find support if required. And according to the screenshot of the TIOB language index, that is definitely true for Python. So although Python was not the main language used in high-energy physics, physicists started using Python soon after it was developed. In 1994, a handful of physicists like Jeff Templon started using Python. These were just small scripts for their own toy projects, but not really used on a large scale. After 3 years, Fermilab, one of the largest national laboratories in the US, published a paper about using Python as an extension language for the D0 experiment. They published this at CHEP, which is the flagship conference for computing in high-energy physics, so it was kind of a big deal. After a year, in 1998, Jeff Templon published a paper titled Python as an Integration Language at the Physics Department of the University of Georgia. In 2000, Python slowly started being adopted on a larger scale. There were 2 talks presented at CHEP about Python, titled Dynamic Graphical User Interfaces using XML and JPython from Fermilab, and IDA LHC++ User Interface in Python from CERN. In 2001, Philippe Canal, who is one of the core developers of one of the most widely used software libraries today, gave a talk summarizing the data analysis and visualization track at CHEP, where he emphasized the usage of Python in high-energy physics. By 2003, experiments had started putting Python in some of the analysis frameworks. And once it is in an analysis framework, most of the people in that experiment start using it. So let's say by 2003, physicists had started seriously using Python for their analysis. But even so, C++ was still the main language being used. So this is a plot created by Jim Pivarsky, who coined the term Year of Python, as according to this plot, in 2019, Python usage in high-energy physics trumped the usage of C++ for the first time. And okay, so this plot should not be relied on solely because this is based on the GitHub repositories of users who have forked a well-known high-energy physics repository on GitHub called CMSSW. But this does give us an indication of where things are headed. In the past, there have been mainly two languages that have dominated in the field of high energy physics. There was Fortran up to early 1990s. There was this whole ecosystem built in Fortran with PAW, HBook, and Zebra. And then in the early 1990s, Root was created, which was written in C++. And Root is still being used to this day extensively. I'm going to talk about more about Root in the next few slides, but let me complete by saying that I am optimistic that Python is the language of the future. So, how do high energy physics people work with data? Every high energy physics researcher uses Root. So, Root is a modular scientific software toolkit. It provides all the functionalities needed to deal with big data processing, statistical analysis, visualization, and storage. It is mainly written in C++. And when I say that it provides all of the functionalities, it really does provide all of the functionalities. It provides everything from plotting graphs to machine learning libraries and data frames for storing columnar data, all in this one monolithic package called Root. And Root is probably the primary reason for the dominance of C++ in high energy physics. So, Root was built in the mid 1990s by Radium Brun and Fons Radmakers. It convincingly, quite convincingly, replaced PAW and the Fortran ecosystem in high energy physics. I don't think any people use PAW or HBook or Zebra today, or I mean, even if they do, it is probably to maintain some sort of backward compatibility with data that was recorded back in the 1980s. Um, so root is probably the file format, or to be more accurate, the largest open source file format storing the largest amount of data. Root is developed by a small team, currently led by Axel Norman at CERN, who work quite actively on maintaining and developing it. Um, I think to this day, computing and high energy physics is quite synonymous with root. It's hard to imagine both of them being separate. I think you might have heard of the discovery of the Higgs boson at CERN in 2012. If you look at the slide at the bottom, it is the official atlas plot created by Root that was used to represent the existence of the Higgs boson. So Root is quite important in high energy physics research. But many people asked for a Python interface. I'm not surprised. So Root has Python wrappers around its C++ code and they call it PyRoot. But the root code base is actually quite large. I think it consists of millions and millions of lines of code. If you look at the contribution statistics to the right of the slide, you will notice that each of these developers themselves have more than a million lines of code added to the code base. And this doesn't even count people who contributed before 2000. So how does one handle this? You don't really expect people to add Python bindings around each class for millions of lines of code. So Root came up with something called cppyy. So cppyy creates dynamic bindings, and this was initially developed by Wim Lavritsen and quite deeply integrated with Root, even though it does exist as a separate library. So cppyy is quite an interesting thing, which I think is quite unique to the high energy physics world. Uh, you might be surprised to know that root actually just comprises of three main files for generating the Python bindings. It's root.py, cppyy.py, and pythonization.py. Root doesn't have separate files for each C++ class to link it to Python. So this is quite convenient if you think about it. Um, and although it is deeply integrated with root, the author, Wim Lavritsen, is currently trying to develop it to be a standalone library, and I think that once it is fully developed, it might be quite revolutionary for fields other than high energy physics. So there is another way to read and write root files. It is called uproot. So uproot is an alternate implementation of root.io in Python. Even though PyRoot is improving day by day, and the root developers are working on something called experimental PyRoot to solve some of these issues, but there are still some issues that users would run into if they tried using pyroot today. There are object ownership issues between the C++ and Python root code. Pyroot is not really completely Pythonic like you would expect it to be, and it is kind of slow to deal with certain types of data. And here we are not really talking about Python slow, we are talking about slow as in slower than even naive Python. So that is why uproot was written to solve some of these issues. And since it is written completely in Python, it implicitly solves the first two issues out of the pack. And although rewriting something in Python might be quite difficult, it is not impossible. Uproot was actually created by a single full-time employee, Jim Pewarsky, and his student me, and also, of course, helped by many volunteers who still push commits and send pull requests to help in maintaining and developing it. Uproot is one of the most widely used Python packages in high-energy physics, although it is relatively quite new. Okay, when I say relatively, it started being written by Jim in late 2017. But when you think about it, the other library that came before it, or rather the library that is still being used, or the main library root, was developed in mid 1990s. That so compared to that, uproot is really quite new, and it is really just Python. If you look at the graph, or rather the bar at the top, you will notice that all of it is just Python and Jupyter notebooks. The 1.5% C that is present is a developer tool that I wrote that is just to be used for and by developers, and users don't interact with it. And if you look at the graph, you will realize that uproot is used equally up there with the other industry tools for scientific computing like NumPy and SciPy. So it is quite popular. And this graph was plotted from scientific Linux usage only. Scientific Linux was created in Fermilab for use by physicists, and we rejected the other operating systems because those contain some noise with data from batch jobs and such. So this is quite more accurate than other OSs. So Python is not so slow, contrary to popular belief. But that is only when used with libraries like NumPy or Numba or other libraries. I am sure there are a bunch of them out there that improve performance or release the GIL or something. And okay, so in this benchmark with the time and the speed up, it is performed on a code computing a fractal. If you want to look at the code, there is the link to the notebook at the bottom. If you look at this closely, you will notice that the vectorized NumPy performs almost as fast as C++ root, with vectorized NumPy at 30 times the speed of naive Python and root at 32 times the speed of naive Python. And if you use something like Numba, then it is much faster than C++ root, with the compiled by Numba benchmark at a 90 times speed up, with root just at 32 times. But this is to be taken with a pinch of salt because this is for just one piece of code that we chose, especially to show that Python does not mean that it is slow. And I'm sure that for more general uses, they would be at par, or C++ root would be faster than uproot. So this is a tool that was developed outside of energy physics, unlike a lot of the things that I've been talking about. And I think most of you might have heard of this already. PyBind 11 is a very popular tool that is used in industry and even by hobbyists, I would say. If you look at the GitHub stars, there are 7,000 stars. That reminds me, I should probably go and start it myself since I started using it. Um, and if the stars are 7,000, I'm sure the actual number of people that are using it are a bunch more. By bunch, I mean like exponentially more. Um, and so my point in this slide is not to talk about PyBind 11 itself, but how we can use PyBind 11 for high energy physics software. So why would a high energy physics researcher use PyBind11? It is easy to wrap existing C++ code in PyBind11, and it is not always easy to vectorize all operations implemented in Python, even if you're using a library like NumPy. Although we showed that Python does not necessarily mean false, it was for a particular process, like I said earlier. In general, I guess naive C++ code will always be faster than naive Python code. There might be a few exceptions, but yeah, C++ faster than Python. Um, and I'm going to again talk about awkward array, the library that I mentioned at the start of this talk. So awkward array was initially written solely in Python, but it was recently implemented in C++ and PyBind11 with a lot of success. Even though it's still in development, a lot of physicists have already started using it. So there are multiple reasons why the author decided to rewrite it in C++ and 5.11. The original NumPy interface was hard to extend and maintain, and also the author conducted a survey where he asked physicists what they required, and they said that although they appreciate a NumPy-like interface and they like to use it, but they still sometimes would need an interface for imperative programming. There are other high-energy physics libraries except Awkward Array that are using 5.11 already. For example, the Boost histogram library, PyHepMC, and Goofy. This brings me to the Scikit-HEP project. So the Scikit-HEP project is meant to contain all Python tools that might be required for research in high-energy physics. There are a lot of active developers building tools in Python for use in high-energy physics that are housed under this project. And since all of the tools are in Python, one can actually consider it to be a modularized toolset. And physicists can pick and choose the library that they need for their current use case at that point of time. And then once they're done with that and they need to do something else, they can just move over to another library. And also, some of the libraries under Scikit-HEP are extensions to industry developed libraries, and this means that it does not require a lot of reinventing the wheel for high energy physics uses. And the Scikit-HEP project also has an actively monitored GitHub channel. So if you want to reach out to people in this community, I have the name of the channel in the slide. So please go ahead, and I'm sure that you'll find a lot of people willing to talk to you. So this is a list of currently active packages under the Scikit-HEP project. This slide was presented by Eduardo Rodriguez at CHEP 2019. If you look at the slide closely, you will see that there are tools for everything. There are tools for tracking particles and decays, for histogramming, event processing, fitting, simulation, everything. The Scikit-HEP project is growing with many new packages still coming up. This is not very surprising as it mirrors the Python growth plot that I had shown in an earlier slide. This is made more evident by the fact that if you look at the slide, you will notice that some packages are tagged as new packages. These were developed after CHEP 2019, so they are quite new. I think the recent advances in the fields of machine learning and deep learning have played a major role in the shift from root and C++ to Python in the form of pyroot and uproot. Root has its own machine learning library, TMVA, but in my personal opinion, I think it cannot really measure up to industry standard libraries such as PyTorch and TensorFlow. But high energy physicists are open to change and invite people from industry to speak at their conferences. For example, Somit Chintala, one of the creators of PyTorch, was invited to speak at ACAT 2019 about how physicists can use PyTorch for their research. So far, this has all been from the perspective of a computer science student, me. But let's see what high energy physicists have to say. This is a slide by Chris Bird that he presented at PyHep 2018. He says that 90% or more of the code that he writes will probably never be used again. The time it takes to write and execute his code is important to him. Okay, C++ is fast, but it probably takes longer to write C++ code than Python code. So in certain cases, the benefit of performance in C++ might actually be costing him time over writing something in Python. Python is designed to be readable. It is quite easy to read when compared to other languages like say C++. His last point elaborates on what I have already discussed in some earlier slides. So we can see that there are compelling arguments that make some physicists want to switch over to Python from C++. So far, I have been talking about Python usage in high energy physics, but I would like to briefly talk about Python usage in other physics fields. So I think the physics field having the most usage of Python is astronomy. Astropy is a really well-known library. It is a little similar to Scikit-HEP, although I would say that it has more adoption than Scikit-HEP, at least at this current stage. And if you look at the plot on the slide, you will notice that when software is mentioned in astronomy publications, the tendency for it to be written in Python has exponentially grown over the years and completely dominates over other languages used for writing software in astronomy like IDL, MATLAB, or Fortran. So in my mind, there are three main ways to push Python adoption in high energy physics. So this slide describes what I think should be the way to uh, promote Python for libraries that already exist. So one could use cppyy to create Python bindings. And this is definitely the easiest way to do it because like I said, you just need a few Python files to do all of the binding. But this may not be ready for generalized use. A more common option, as in used outside of energy physics, is using PyBind 11. But again, it's tedious to wrap entire code bases in PyBind 11. But then again, it's easier than rewriting the entire code base in Python. And since it is used outside of energy physics, you will find people that have faced the problems that you face while trying to use PyBind 11 to wrap all of your code. So help might be more easily available. And the third option is rewriting it all in Python. And this might be a little more difficult than the other two options, but this can be done, as demonstrated in uproot. But then again, it's impossible to rewrite all of the C++ physics libraries in Python. For high energy physics libraries that have not yet been written or are being planned to be written in the next few days, this is what I recommend. So one can use cppyy, but again, it's not really ready for generalized use yet, in my opinion. And if you try using it, you might run into some unsurmountable problems. The other option is using PyBind 11, and using PyBind 11 probably involves writing a lot of additional code to in addition to your C++. But then again, it is not very difficult to do this, and this is definitely the go-to strategy if C++ speed is required. And the third option is rewriting the entire thing in Python. And for a new library, this might be preferred because for a physicist who does not know C++ or Python, or any language for that matter, using Python might be easier because it is easier to learn than other languages. But then again, if performance is critical, then it is recommended that you only write it in Python if you are familiar with the ecosystem and libraries such as NumPy and Numba that would help you get the performance that you desire. To conclude, I would like to say that it is evident from my talk that Python is a popular language. Even in sciences like high energy physics, where performance is critical, Python is quite readable compared to other languages like C++. And this is something that people whose primary interest is not learning a new programming language would desire. And according to me, Python is most definitely the natural bridge to machine learning and other statistical software written outside of high energy physics. Although there are some alternatives in other languages, the most popularly known and used ones are definitely in Python. Newcomers to high energy physics would probably know about industry standard tools like pandas and TensorFlow as compared to their root alternatives like RData frame and TMVA. So, in my firm opinion, I believe that Python is here to stay in the high energy physics community for the foreseeable future. So, several people have helped me with my talk. I would really like to acknowledge their help. Jim Pivarsky, Jeff Templon, Henry Schreiner, Eduardo Rodriguez, and many others who have motivated me and helped me write my slides. So here are some links, mostly talks, that you might want to look at if you want to know more about how we use Python for high energy physics research. And on this slide, I have the links to the projects that I mentioned in my slides if you want to go ahead and look at the source code and maybe even contribute to some of them. That brings me to the end of my talk. If you want to contact me, you might do so at reekdas@gmail.com. And if you want to view my work, you can do that at GitHub under the name Reekdas. Thank you for listening to my talk.